This is one of two videos talking about inner products and norms. This is the overview slide for the two videos. I'll spend about 5 minutes going over it before going over the first two topics in more detail and with more examples, and then introducing the other topics, the other two topics that are covered in the second video. We will start with a review of the dot product for vectors in Rn that you probably learned in vector calculus. So for a vector x and a vector y, we take the dot product, and that's the sum of component by component multiplication. The dot product has these important properties which we will review. Next, we will define the inner product, which is an abstraction of the dot product. In other words, it's the important properties of a dot product. So we define an inner product on a vector space V as a function that takes each ordered pair, UV, vectors of the vector space, to a number in the scalar field. And we denote that number with the brackets. This is the inner product of UV. And the inner product, to be an inner product, a function must have the following properties. First, positivity. Second, the inner product of a vector with itself is equal to 0 if and only if v is equal to 0. Third, additivity in the first slot. And fourth, homogeneity in the first slot. And finally, conjugate symmetry. And we will look at these properties in lots of detail in the main part of our video. Once we've looked at the inner product, we can define the inner product space, which is just a vector space, along with an inner product defined on that vector space. We will look at the inner product spaces and their properties. We will look very briefly at the definition of a norm and orthogonal vectors and cover those in more detail in our second video, our next video. So that wraps up our overview, so we're ready to go back and start with a closer look at the dot product. You most likely have seen the dot product for vectors in Rn in vector calculus. So if you have vectors x and y, where x is the vector with coordinates x1, x2 up to xn, and y is the vector with coordinates y1, y2 up to yn, then x dot y is equal to the first coordinate of x times the first coordinate of y, plus the second coordinate of x times the second coordinate of y, on up to the nth coordinate of x times the nth coordinate of y. And you can see that this dot product will always produce a scalar. And remember, in vector calculus, there were two ways to multiply two vectors. One was the dot product, which produced a scalar. The other was the cross product, which produced a vector. But we're only concerned in this class with the dot product. It has the following properties. You can see that when x is dotted with itself, it's always going to be greater than or equal to 0, since you're going to be having squared terms for each of these terms. Also, you'll see that x dot x will equal to 0 if and only if x is equal to 0. Also, since multiplication is commutative, you will see that x dot y is equal to y dot x for all x and y in Rn. And finally, if y is a fixed vector from Rn, then the mapping from Rn to R that sends x in Rn into x dot y is a linear mapping. In other words, the dot product is a linear mapping. And when n is equal to 2 or 3, in other words, we're in R2 and R3, we have something called the norm of x, which we denote with these kind of double absolute values. So the norm of x is equal to the square root of x dot x, which is equal to the square root of x1 squared plus x2 squared up to xn squared. So this is your normal, or the idea of length of a vector x that you're used to. Because we're going to be talking about complex conjugates and doing some proofs, I have some properties here of complex numbers that'll come in really handy. So if you have a complex number z, which is equal to a plus ib, a and b are real numbers, and then this number I multiplies b. So this is the imaginary part, b is the imaginary part, and a is the real part. We define the absolute value, which we have the straight line for. Absolute value of z is equal to a squared plus b squared, all square rooted. We define the complex conjugate of z is equal to a minus ib. In other words, the imaginary part has a negative sign in front of it. From there, we see that the absolute value squared is equal to z times its complex conjugate, and you can do the arithmetic and verify this is true. We also have, if we have a vector z and we have its complex conjugate and then take the complex conjugate of that, so 2 complex conjugate, we just get back our original vector z. Also, the absolute value of the complex conjugate of z is equal to the absolute value of z, and you can do that calculation algebraically and verify that for yourself. You'll also see that the complex conjugate of z1 plus z2, you can break that up to the complex conjugate of z1 plus the complex conjugate of z2, similarly with the minus sign. And when you have multiplication, so the complex conjugate of z1 times z2 is equal to the complex conjugate of z1 times the complex conjugate of z2. Similarly for division, so if you have the complex conjugate of z1 divided by z2, that's equal to the complex conjugate of z1 divided by complex conjugate of z2, provided that z2 is not equal to 0. And again, because the inner product has a symmetry with complex conjugates, these properties will be useful when you're trying to prove something is an inner product. Last, we have this definition of the norm of a complex number, which we denote with the double bar, so different from the absolute value. But that's equal to the square root over here of the absolute value of the first component, z1 squared, plus the absolute value of the second component squared, all the way up to the nth component, absolute value squared. So the absolute values are needed so that this norm is non-negative, and we want to think of this norm as the inner product of z with itself. Now we're ready to look at the inner product, which is an abstraction of the dot product. So first, we'll define the inner product on V as a function that takes each ordered pair of vectors uv from the vector space to a number which we denote with the inner product uv. So it takes this pair of elements to a number, a scalar number in F. And it has the following properties. First, it has positivity. So the inner product of V with itself is greater than or equal to 0, and it's exactly equal to 0 if and only if V is equal to 0. So that's these two properties here, this first one and the second one, positivity, and also this other thing equaling 0. Our next two properties, additivity in the first lot and homogeneity, that is corresponding to this idea that the dot product is linear. So here what we have is additivity in the first slot. So it's a little bit different because now we're also possibly talking about not just vectors in Rn, but general vectors. So additivity in the first slot. So when you have the inner product of u plus v with w, that will equal to the inner product of uw plus the inner product of vw. Homogeneity in the first slot, that's when we have the multiplication by a scalar alpha times u, inner product with v, is equal to the scalar alpha times the inner product u and v. And last, we have conjugate symmetry. And this corresponds to this property here, property number 3, where we have this commutativity in the dot product of x dot y is equal to y dot x. We don't have quite the same thing here for the inner product. Remember, these are general vectors, and vectors that might involve complex numbers, so not just real numbers. The inner product of uv is almost equal to the inner product of vu, so there's almost this commutativity, but for vu you have to take the complex conjugate. However, if u and v are real numbers, then this complex conjugate of the inner product of vu is just equal to the inner product of vu, because essentially if you're dealing with real numbers, the complex conjugate of a plus ib is simply equal to a plus ib, because if you're dealing with real numbers, b is equal to 0. So you just have a equals a. So if u and v are real, have only real numbers, then we have this commutativity of the dot product. In this next example, I'm going to use the dot product for Rn to illustrate some of these properties. Afterwards, I'll do some other examples with other inner products and showing how you can prove that they meet these qualifications or have these properties. For this example, I'm going to look at R2, and I'm going to use the vectors u equals 3, 2, v equals 1, 2, and w equals -1, 0. I can start with the first property, positivity, and look at the inner product of v with itself. That is 1, 2 dotted with 1, 2. So we have 1 times 1 plus 2 times 2 is equal to 5. And you can see because we have these squares here, we're always going to get a positive number. So if we look at the inner product of w with itself, it's -1 dotted with -1, 0. Then we have the -1 times -1, which is positive, 0 times 0, which is positive. We end up with 1, which is positive. The next property I will look at is additivity in the first slot. So we're going to look at the inner product of u plus v with w. So here I have u plus v, so 3, 2 plus 1, 2, inner product with w, -1, 0. So my 3, 2 plus 1, 2 is equal to 3 plus 1 is 4, and then I have 2 plus 2 is 4, inner product with -1, 0, so I have 4 times -1 plus 4 times 0, which gives me -4. Then I can look at the other side of the equation for my additivity in first slot and calculate the inner product of uw added to the inner product of vw. So the inner product of uw, that is the inner product of 3, 2 with -1, 0 plus the inner product of vw, that's the inner product of 1, 2 with -1, 0. Here I get 3 times -1 plus 2 times 0 plus 1 times -1 plus 2 times 0, which also gives me -4. So both sides of these two sides of the equation here, that is the u plus vw, is equal to uw plus vw. The next property we'll look at is homogeneity in the first slot. So I'm going to set alpha equal to 2, and I'm going to look at the inner product of alpha u with v. This is alpha 2 times u, 3, 2, inner product with v, 1, 2. So we have 2 times 3, 2, which is 6, 4, inner product with 1, 2, so we get 6 times 1 plus 4 times 2, which is equal to 14. Looking at the other side of the equation, I can look at alpha times the inner product of uv, that is 2 times the inner product of 3, 2, and 1, 2. So I get 3 times 1, and then 2 times 2, which is 4, multiplied by my scalar 2, which is equal to 14. So you can see both sides of the equation of our homogeneity in the first slot is satisfied. The next property we will look at is conjugate symmetry. So we'll look at the inner product of uv, that is the inner product of 3, 2, and 1, 2, and we get 3 times 1 plus 2 times 2, which is 7. Compare that to the complex conjugate of vu, the inner product of vu. So we have the inner product of 1, 2 with u, 3, 2. So that's 1 times 3 plus 2 times 2, which is 7, and we take the complex conjugate. There's no imaginary part, so that's simply equal to 7. And you can see that the dot product follows the conjugate symmetry property of inner products. What if u and v had complex things? So now we're not talking about Rn at this point. We're talking about Cn. So u, let's set that equal to 1 plus 3i, 2, and v is equal to I, 2i plus 1. So the inner product now of u and v is equal to 1 plus 3i times I plus 2 times 2i plus 1. After some algebra, you'll get -1 plus 5i. If you compare that to the complex conjugate of vu, that is 1, 2i plus 1, inner product with 1 plus 3i, 2, and then take the complex conjugate, you're going to get I times 1 plus 3i, and then 2i plus 1 times 2. It's really the same form, just these factors are rearranged. So you totally expect then that the complex conjugate will be off over here, because instead of plus 5i, now you get a -5i. So these two are not equal. So what we will say is while the dot product for Rn is an inner product, we didn't prove that, but we saw some examples that the different properties hold, and we can prove it, but we're not going to. But what we will say is the dot product over Cn, so if our vectors have complex numbers, then we lack conjugate symmetry, and therefore this dot product definition we have here for Rn, it won't work on Cn. We will not have an inner product. What we are going to do now then for Fn, in place of the dot product, we're going to define what we call the Euclidean inner product on f of n by the inner product of a vector w and a vector z. Both of these can have complex numbers, is going to be the sum of component by component multiplication of the component of w multiplied by the corresponding component of z's complex conjugate. So on the next slide, we'll take a closer look at this Euclidean inner product and prove that it does indeed satisfy all these properties of an inner product. Just to repeat this point, for vectors in Fn, that is vectors that is an n tuple, so vectors that look like w1, w2 up to wn, or z1, z2 up to zn, where these components here can be complex numbers, we don't use the regular dot product that we learned in vector calculus, but we use this new inner product, and it's defined as component by component multiplication, except this second vector here, we're going to use the conjugate. What we are going to do for this example and several examples after is we're going to look at different definitions over here, and we're going to prove that this function here does satisfy the conditions of an inner product. So therefore, this proposed inner product is indeed an inner product. For my proofs, I'm going to take three vectors u, v, and w, and I'm going to allow them to have complex components. So u I'm going to write as a1 plus ib1, its second coordinate will be a2 plus ib2, up to its nth coordinate is an plus ibn. My vector v, I'm going to designate with c1 plus id1, c2 plus id2 up to cn plus idn. And vector w is going to be f1 plus ig1, f2 plus ig2 up to fn plus ign. And of course the a's, the b's, the c's, the d's, the f's, and g's, those are all real numbers, but because of the ib1 or the id2 or the fgn, the vectors have complex or potentially complex components. And now if I want to take the inner product of u and v, using this definition here, I'm going to multiply component by component, but the second vector, I'm going to use the complex conjugate. So uv, I'm going to take the first coordinate of u multiplied by the complex conjugate of the first coordinate of v. So that would be c1 minus id1. Then for my second coordinate, I have a2 plus ib2 times c2 minus id2, the complex conjugate, up to abn plus ibn, cn minus idn. Now if I want to show this first property, positivity, I need to take the complex conjugate of a vector with itself and show that it's greater than or equal to 0. So I'm going to take the complex conjugate of v with itself. So I'm going to take the first coordinate of v and multiply it by the complex conjugate of the first coordinate of v. So I have c1 minus id1 plus c2 id2 times c2 minus id2 up to cn plus idn times cn minus idn. When I do the algebra, here I'm going to get c1 squared. Here I get minus I c1 d1, but I also have here plus I c1 d1. So those cancel out. And then these two, my two i's give me a negative, which cancels with this, which will give me a positive d1 squared. I go down for c2, and I get c2 plus d2 squared for this term. And my final term, I'll get cn squared plus dn squared. And now because I have a sum of squares, this necessarily has to be greater than or equal to 0. To show this second property, that the inner product of v with itself is equal to 0 if and only if v equals 0, we can now take our v inner product with itself. We have that equal to c1 squared plus d1 squared up to cn squared plus dn squared equals 0. Well, this necessarily means, since these are all positive, there's no cancellation because of some positive canceling with the negative, it must necessarily mean that all the constants c1, c2 up to cn is equal to 0, and all the constants d1 up to d2 up to dn is equal to 0, which means our vector v is equal to 0. Now we're ready to look at additivity in the first slot. So we'll look at the inner product of u plus v with w, and we want to verify that's equal to the inner product of uw plus the inner product of vw. We will start with the inner product of u plus v with w. So u plus v, here's our u and here's our v, will be our a1 plus ib1 plus c1 plus id1. And then our second coordinate is going to be a2 plus ib2 plus c2 plus id2 up to an plus ibn plus cn plus idn. And we're going to inner product that with w. I was going to group my a1s, my basically real parts, and my imaginary parts together, but keeping them this way is going to be easier to separate it back out to this right-hand side of the equation. Now doing the inner product with w, I have my first coordinate, my a1 plus ib1 plus c1 plus id1, and I'm going to multiply it by the complex conjugate of the first coordinate of w, which is this f1 minus ig1. Now I need to add that with my second coordinate, my a2 plus ib2 plus c2 plus id2, with the complex conjugate of the second coordinate of w, which is f2 minus ig1. And I go and do this for the nth coordinate an plus ibn plus cn plus idn multiplied by fn minus ign. Using just regular operations, the distributive operation, I'm going to multiply my f1 minus ig1 by these first two terms and add that to my f1 minus ig1 times my second two terms. So I have a1 plus ib1 times f1 minus ig1 plus c1 plus id1 times f1 plus ig1. That's coming from here. I just used my distributive property to kind of separate things out, because ultimately I want to get it to look like this right-hand side of the equation where I have the inner product of uw plus the inner product of vw. So this is beginning to look like uw plus the inner product of vw. I do the same for my second term. I distribute my f2 minus ig2, and I multiply it first times a2 plus ib2, and then I multiply it c2 plus id2 over here. And then finally, I do this for this last term. I multiply my fn minus ign first times an minus ibn, and then second times my cn plus idn. I switched my colors around. I grouped everything. These ones in yellow, those are the terms that look like u. In other words, they have the a's and b's. So I group those together first, and I'm multiplying them times my terms from w bar. Then I have my red terms. I group those terms together. The red terms are the ones that come from, where did the c? They come from v, because they're the ones with the c's and d's, and I'm multiplying them times my w bar. And those are these terms here. So eventually what I get is this set of terms is equal to uw, and this set of terms over here is equal to the inner product of vw. And therefore, I have shown that my inner product of u plus v with w is equal to the inner product of uw plus inner product of vw. The next property we would like to prove is homogeneity in the first slot. That is, the inner product of a scalar alpha times u with v is equal to the scalar alpha times the inner product of u v. Looking at the left-hand side first, the inner product of alpha u v is equal to, now my alpha u, just every term of u gets multiplied by alpha. So alpha a1 plus ib1, alpha a2 plus ib2, up to alpha an plus ibn, inner product with v. So my first coordinate, my alpha a1 plus ib1, gets multiplied by the complex conjugate of my first coordinate of v, that's c1 minus id1. My second coordinate now is my alpha ab2 plus ib2 multiplied by the complex conjugate of the second term of v, which is c2 minus id2. And I do this all the way to an. So alpha an plus ibn times cn minus idn. At this point, we're down to algebra, but you can see we have an alpha in front of all of our terms. So we can factor that out using regular distributive property. And then we have alpha times all of our terms, our a1 plus ib1 times c1 minus id1, our second term a2 plus ib2 times c2 minus id2, up to the nth term an plus ibn times cn minus idn, which here now we have alpha, and this whole thing here is equal to the inner product of u and v. So we have shown or demonstrated homogeneity. The last property we have is conjugate symmetry. So we want to show that the inner product of uv is equal to the complex conjugate. This is over the whole entire inner product. Complex conjugate of the inner product of vu. And since we already have uv over here, I'm going to start with the inner product of vu, which is c1 plus id1 times, now u, we need to take, since it's our second vector, we need to take the complex conjugate of its coordinates, right? Using this definition here for our inner product. The second vector has the complex conjugate. So we're going to have v, which is c1 plus id1, the complex conjugate of the first coordinate of u, which is a1 minus ib1. We have the second coordinate of v, which is c2 plus id1, times the complex conjugate of the second coordinate of u, a2 minus ib2, up to cn plus idn, an minus ibn. Now I'm going to take the complex conjugate of this whole thing here. So I have c1 minus id1 times a1 plus ib1. Here I'll have c2 minus id2 times a2 plus ib2 up to cn minus idn times an plus ibn. And you will recognize this if you just kind of swap the order, and we can do that because multiplication is commutative. Swap the order of these two, swap the order of these two, swap the order of these two, and again we can do that because at this point we're just multiplying complex numbers and we can swap the order. There's commutativity. So we have that's equal to the inner product of u and v. And therefore we have shown that this function here that we were given, so we were given this function as a proposed inner product, we have verified that this function satisfies all the conditions of being an inner product, and therefore this function on the two vectors is indeed an inner product. Our next example is if c1, c2 up to cn are positive numbers, define the inner product of the inner product of w with z is equal to c1 times w1 times the complex conjugate of z1 plus c2 times w2 times the complex conjugate of z2 up to cn times wn complex conjugate of zn. Because this problem is so similar, or this function is so similar to our last inner product, the only difference now is that we have these coefficients multiplied out. I'm not going to do the whole problem of verifying all of these properties, but I will choose two of them to verify. And I'm also going to start by writing our arbitrary vectors u, v, and w, and defining what the inner product looks like with this definition here. So I'm going to have the inner product of u and v is equal to, in this case I have u and v, is equal to c1 times the first coordinate from u times the complex conjugate of the first coordinate from v. So I have c1 a1 plus ib1 times c1 minus id1. And my second coordinate is going to be c2 a2 plus ib2 times the complex conjugate of the second term of v, which is c2 minus id2, all the way up to cn times an plus ibn times cn minus idn. The first property I'm going to demonstrate is positivity. So I'm going to look at the inner product of v with itself. Here I have our definition, C1, A1 plus IB1 times the complex conjugate of the first coordinate of V, which is A1 minus IB1, plus C2 times A2 plus IB2 times A2 minus IB2 up to the nth term Cn, An plus IBn times An minus IBn. When I do my algebra, what I get is C1 times A squared plus B squared plus C2 times A squared plus B squared plus Cn times An squared plus Bn squared. These terms here, since they're the sum of squares, are all positive. And since C1, C2 up to Cn, these are all positive numbers that was given to us when we defined our inner product. That means that this summation here must be greater than or equal to 0. The next property I will demonstrate is additivity in the first lot. So I'm going to show the inner product of u plus v with w is equal to the inner product of uw plus the inner product of vw. So I'm going to start again with the left-hand side, looking at the inner product of u plus v with w. So here I have u plus v, which for my first term, I'm going to get a1 plus ib1 times c1 plus id1. For my second coordinate, I'm going to get a2 plus ib2 plus c2 plus id2, and my nth coordinate is going to be an plus ibn plus cn plus idn, and I want the inner product with w. And I just realized I'm going to have trouble because I used C1 here, and my constants are called C. So I am going to maybe underline my constants. No, how am I going to do this? I'm going to make my constants with a star, an asterisk next to them. So here you can see I've rewritten my constants with the asterisk next to them. So my new definition of my inner product is my C1 asterisk times W1, a complex conjugate of Z1, C2 asterisk W2, Z2 with a complex conjugate up to Cn asterisk times Wn times the complex conjugate of Zn. So now I can define my inner product of my u plus v and w. So I'm going to have my C1 times my first coordinate of u plus v, which is a1 plus ib1 plus c1 plus id1, times my complex conjugate of my first coordinate of w, which is f1 minus ig1. I hope I put i's on my other ones, ig1. My second term will be my c2 star constant times my second coordinate of u plus v, which is a2 plus ib2 plus c2 plus id2, times, gosh, I totally forgot. Over here I need to multiply by f2 minus ig2. That looks like a 12, g2. And then I go up to my nth coordinate, which is my cn star, times an plus ibn plus cn plus idn, times my complex conjugate of my last coordinate of w, which is fn minus ign. Now, very similar to the last problem, I can use the distributive property to take out the c1, a1 plus ib1 in my f1 minus ig1, and then add that to c1 star, c1 plus id1 times f1 minus ig2. I skipped the second term and I went straight to the last term because you could probably see the pattern. Cn times an plus ibn times fn minus ign plus cn times cn star times cn plus idn times fn minus ign. I can then gather all my terms with u and w together, which I've underlined in yellow. I can gather all my terms of vectors from v and w, which I've underlined in green together. And what you will see is the yellow terms give me the inner product of u and w. And that will conclude our demonstration of the property of additivity in the first slide. And those are the two properties, the positivity and additivity in the first lot, that I will do for this example. Our next example is to define an inner product on the vector space of continuous real-valued functions. I underline this because sometimes I forget and it won't work if it's not real-valued. So continuous real-valued functions on the interval from -1 to 1. We define that as the inner product on f and g is equal to the integral from -1 to 1 f of x g of x. And we will demonstrate that this definition, this function definition, satisfies all the conditions of an inner product and therefore is a valid inner product. So we will start with positivity. So we want to show that the inner product of f with itself is greater than or equal to 0. And by this definition here, that means we want to show that the integral from -1 to 1 of f of x times itself is greater than or equal to 0. But this integral, f of x times f of x, is a square, which is always positive, and the integral of a positive function is always positive. So therefore, the integral from -1 to 1 of f of x squared dx is greater than or equal to 0. We can continue with our second property where we want to show the inner product of f with itself is equal to 0 if and only if the function f is equal to 0. But if we think of this integral as the area under the curve, and we know f of x squared is always positive, there's no way that any positive integral can be kind of canceled out by negative integral to get 0. That must mean the only way the area under the curve is 0 is if f of x itself is equal to 0. So that's our second property. Our next property is additivity in the first lot. That is, the inner product of u plus v with w is equal to the inner product of uw plus the inner product of vw. So using our definition of our integrals, we're going to work on this left-hand side, the inner product of u plus v with w. That's the integral from -1 to 1 of our function u of x plus v of x multiplied by our function w of x. By algebra, we can multiply our functions using the distributive property, so we get the integral of u of x w of x plus v of x wx. A property of integrals, because integrals are linear, you can separate out this, so we have the sum of the integral u of x wx plus the integral v of x wx. And you can see that this first integral is simply the inner product of u with w. The second integral is the inner product of v with w. So we have demonstrated additivity in the first slot. Scalar alpha times u with v is equal to the scalar alpha times the inner product of uv. So working now on the left-hand side of our equation, using our definition for our inner product of alpha u with v, we're going to have the integral from -1 to 1 alpha u of x times v of x, which, using properties of integrals, we can pull out this scalar constant alpha, and we get alpha times the integral from -1 to 1 u of x v of x, which is simply equal to alpha times the inner product of u and v. And hence we have demonstrated homogeneity in the first slot. I initially had problems proving conjugate symmetry, that is, that the inner product of uv is equal to the complex conjugate of the inner product vu. And the reason why I had problems is because I failed to take note that we're looking at real valued functions, and this is super important because it becomes a very easy problem once you know you're working with real valued functions. And for whatever reason, I decided to name my functions f and g, probably because I was looking at the inner product rather than for naming them v and u as I did in my previous example. But I started with this right-hand side. I wanted to look at the complex conjugate of vu. So I'm going to look at the complex conjugate of the inner product of g and f, which is the complex conjugate of the integral from -1 to 1 g of x f of x dx. Because you can think of the integral of g of x f of x between 2 points a and b, in this case we're between -1 and 1, so pretend like a is negative and b is positive, -1 and 1. You can think of the integral then as the area under the curve, and essentially what you're doing is at each point you're summing up the height, point by point. So if you think of the integral as summing up heights point by point, when you take the complex conjugate, you can actually take the complex conjugate point by point and then sum them up. So in other words, this complex conjugate of the integral is equal to the integral of the complex conjugate of the function inside. At this point, I'm going to use properties of complex numbers, which I had mentioned at the beginning of this video. It seems like so long ago. But anyway, When you have the complex conjugate of the product of two numbers over here, z1, z2, complex conjugate, you can set that equal to the complex conjugate of your first number times the complex conjugate of your second number. So in other words, this expression here is equal to the integral from -1 to 1 complex conjugate of g of x times complex conjugate f of x. And this is the key thing. Since f and g are real valued functions, f and g are real valued, the complex conjugate of the real values are still equal. That is, if you have a real number 3 and you take its complex conjugate, it's still equal to 3 because the complex conjugate of a plus ib is equal to a minus ib. But if b is equal to 0, then your real number is just equal to your real number. So I can drop the complex conjugate. That's what I was missing before. And I was so stuck for over a day. I had to think about it. Now, because multiplication of real valued functions is commutative, you can switch the order of f of x and g of x. So you have the integral from -1 to 1 f of x times g of x, which is equal to the inner product of f and g according to this definition. And we have shown conjugate symmetry. And hence we have shown all 5 properties hold, and therefore this definition of an inner product is valid. I'm going to alter this example now for continuous functions that possibly are complex valued. So we're going to X out this definition here we had for a real valued function, and we're going to change it ever so slightly by making our second function the complex conjugate. This is really similar how we altered the definition of the inner product on Rn, and we defined the Euclidean inner product on Fn, on possibly complex vectors of length n, where we had the second vector then taking the complex conjugate. So totally analogous. And this problem is so similar that I'm not going to do the first 4 properties, but I'm going to concentrate on the conjugate symmetry. That is, the inner product of uv is equal to the complex conjugate of the inner product vu. So again, I'm going to start with the right-hand side, the complex conjugate of gf. This very much mirrors what we did for the previous example over here. So that's equal to the complex conjugate of the integral from -infinity to infinity g of x, and now we have our second function with the complex conjugate on top. That's equal to, now we can move this complex conjugate from the entire integral into the function. So we have integral from -1 to 1, complex conjugate of g of x times the complex conjugate of f of x. Now again, using our property of complex numbers, where we have the complex conjugate of z1 times z2, that's equal to the complex conjugate of z1 times the complex conjugate of z2. So I can separate this out to integral from -1 to 1 complex conjugate of g of x times the complex conjugate of the complex conjugate of f of x. And of course, the complex conjugate of the complex conjugate is just equal to f of x. And so what we have here now, switching the order of f of x and g of x, that's the inner product of f and g, and therefore we have conjugate symmetry. We have our next example, define an inner product on the space of polynomials over the real numbers. So the inner product of a polynomial p and q is equal to the integral from 0 to infinity p of x times q of x times e to the minus x dx. We will first consider positivity, so we want to look at the inner product of a vector with itself. So we have the inner product of a polynomial p with itself, which is the integral from 0 to infinity, this one should be an infinity, of p of x times p of x e to the minus x dx. So what we have is the integral from 0 to infinity of p of x squared. This is a polynomial, and so this is always positive or 0. And then we'll also note that our e to the minus x is always a positive number, which then gives us our inner product of p with itself is always greater than or equal to 0. And also very similar to our last proof where we had an integral, since we wanted to show that the inner product of p with itself is equal to 0 if and only if p of x is equal to 0, Well, since what we're integrating is always positive, the only way for the area under the curve to equal to 0 is if p of x is equal to 0. The next property we have is additivity in the first lot. That is the inner product of u plus v with w is equal to the inner product of uw plus the inner product of vw. Working on the left-hand side now, I'm going to have the inner product of p plus r with another polynomial r. So that's the integral from 0 to infinity, p of x plus q of x times r of x times e to the minus x. But now I can use my distributive property and I can make this equal to p of x times r of x e to the minus x plus q of x r of x e to the minus x. And then by properties of integral, I can separate this into the sum of two integrals. So I have the integral from 0 to infinity p of x r of x e to the x plus the integral from 0 to infinity q of x r of x plus times e to the minus x. And this first integral is equal to the inner product with p with r, and the second integral is the inner product of q with r, and therefore I have shown additivity in the first slot. I'm going to skip homogeneity in the first slot because hopefully you can see the pattern from the previous examples and do this one on your own. But let's look at conjugate symmetry, where we're going to look at the inner product of uv is equal to the complex conjugate of the inner product vu. So I'm going to start with this right-hand side and look at the complex conjugate of the inner product of q and p, which is equal to the complex conjugate 0 to infinity q of x p of x times e to the minus x. And something that we want to note is we're working on p of r, that is polynomials of real valued functions. So very similar, we can move this complex conjugate inside of our integral. This should actually not be here. Let me erase this a little bit. So now we have the integral from 0 to infinity, the complex conjugate of the function q of x, p of x times e to the minus x. Let me also erase this here. And by properties of our complex numbers, we can then also break up, because this is a product of three complex numbers, we can break it up into the product of three complex conjugates. So integral from 0 to infinity complex conjugate of q of x times complex conjugate of p of x times complex conjugate of e to the minus x. Now, because multiplication of functions is commutative, I can switch the order of the p of x and q of x. So I have the integral from 0 to infinity complex conjugate of p of x, complex conjugate q of x times complex conjugate of e to the minus x. And now, because these are real valued functions, we're only putting in real numbers, the complex conjugate is equal to the function. So we have 0 to infinity p of x times q of x e to the minus x. And this is simply equal to the inner product of p and q. So we have shown conjugate symmetry. And now we will move on to talk about inner product spaces and their properties. So we have our definition of an inner product. So an inner product space is simply a vector space along with some definition of an inner product on the vector space. And now that we have an inner product space, we have properties for the inner product space, which very much look similar to the properties of an inner product. The first property is for every fixed u in the vector space V, the function that takes the vector V to the inner product of VU is a linear map from V to F. Second, we have the inner product of 0 with u is equal to 0 for every vector u in V, and similarly, the inner product of u with 0 is equal to 0 for every vector u in V. Next, we have this additivity property, so the inner product of u with v plus w is equal to the inner product of u with v plus the inner product of u with w. Next, we have this homogeneity, so we have the inner product of u with a scalar alpha times v is equal to the complex conjugate of the scalar alpha times the inner product of u and v. And now we're going to take a closer look at each of these properties by proving them. The first property is, if we look at the inner product as taking a vector from the vector space V and then mapping it to a scalar, that this mapping is a linear map. And I copied this criteria for a linear map, so you know what it is we need to prove to show that the inner product is a linear map. The first thing we need to show is additivity, that the transformation on the sum of two vectors is equal to the sum of the transformation on the first vector plus the transformation on the second vector. And then we need to show homogeneity, that the transformation on a scalar alpha times our vector is equal to alpha times the transformation on our vector. And it's not that surprising since our inner product has kind of that additivity and homogeneity built in. But let's do the proof formally. The first thing we want to show is additivity. So our function on two vectors, in this case I'm going to choose v and w. So the function on v plus w should equal to f of v plus f of w. And remember, we're thinking of our function as our inner product, and it's a linear map that takes a vector v and it makes the inner product of v with a fixed vector u. That's also why I didn't choose u here, because u is our fixed vector that we're inner producting. So f of v then, again, is the inner product of v with u, and f of w is the inner product of w with u. So f of v plus w is the inner product of v plus w with u. So let's start writing that down. Working with this left-hand side, f of v plus w is the inner product of v plus w with u. Now by additivity in the first lot, and this is a property of our inner products, and I have this circled over here in green, additivity in the first lot, this is equal to the inner product of v with u plus the inner product of w with u. But this is just equal to f of v plus f of w, so we have shown additivity here, and now we only need to show homogeneity to prove that this is a linear map. So homogeneity is next. For homogeneity, I want to show that f of alpha v is equal to alpha f of v, to the inner product of alpha v with u. This is equal to by homogeneity in the first lot, and now this is homogeneity in the first lot. This is a property, again, of our inner product, and I've boxed it in this yellow. Actually, I didn't quite get the property. I got the name of the property. Here's our property, homogeneity, in the first slot. So this is going to equal to alpha times the inner product of v and u, which by the definition of our inner product is equal to alpha f of v. So we have shown homogeneity and additivity, and therefore shown that the function that takes a vector u to the inner product of vu is a linear map from the vector v to the scalar field f. The next two properties of the inner product of 0 with u and u with 0, we're going to start with b. 0 with u is equal to 0. Since vu is a linear map, this says that linear maps take the 0 vector to the 0 vector. So this 0 vector goes to the 0 vector. And then by complex conjugate symmetry, we get that u0 is equal to 0u. The complex conjugate at this point, since it's equal to 0, the complex conjugate of 0 is 0. So that proves B and C. To prove property D, that the inner product of u with v plus w is equal to the inner product of u with v plus the inner product of u with w. We start by working on the left-hand side, the inner product of u with v plus w, by our property of inner products using complex conjugate symmetry or conjugate symmetry is equal to the complex conjugate of v plus w inner product with u, and that's the whole inner product that's under the conjugate symbol. Using additivity in the first lot, again from inner products, this is equal to the complex conjugate of vu plus the inner product of wu. Using this property of complex conjugates, this is equal to the complex conjugate of vu plus complex conjugate of wu, which by conjugate symmetry is equal to the inner product of uv plus inner product of uw. And therefore, we have proven this additivity property here for an inner product space. Last, we have this homogeneity. So we're going to look at the inner product of u with a scalar a times a vector v. We want to show we can pull out the scalar, but we're going to have a complex conjugate times inner product of u and v. So working on the left-hand side, inner product of u with alpha v is equal to the complex conjugate of alpha v u because of conjugate symmetry of inner products. This is equal to, we can pull out alpha, complex conjugate of alpha times the inner product of vu because of homogeneity in the first slot. Again, that comes from properties of inner products, which is equal to then the complex conjugate alpha times the complex conjugate of vu. And this comes from the property of complex conjugates. And now this is equal to complex conjugate of alpha times the inner product of uv. And that comes from conjugate symmetry, again, of inner products. And therefore, we have proven this homogeneity property of inner product spaces. The rest of our material is going to be covered in our second video, but I'll just introduce first the idea of a norm for a vector in a vector space V. The norm, denoted with these double bars, is defined as the square root of the inner product of V with itself. And we also have this property called orthogonality. So two vectors uv in a vector space V are called orthogonal if their inner products is equal to 0. And I do want to point out from vector calculus, when we're looking at R2 or R3, the inner product was also equal to the norm of u times the norm of v times cosine of theta, where theta is the angle between u and v. And when theta is equal to 90, that's when we have cosine equal to 0, which means the inner product is equal to 0, and we have orthogonal or perpendicular vectors. And finally, in our next video, we will cover the Pythagorean theorem, orthogonal decomposition, the Cauchy-Schwarz inequality, and the triangle inequality. Because this video has gotten so long, I'm going to do a really quick review. We talked about the dot product from vector calculus. So the dot product of a vector x with a vector y is equal to the sum of component by component multiplication. We then defined the inner product, which was an abstraction of the dot product. And we said that an inner product is any function that takes each ordered pair uv, elements of a vector space V, to a number, inner product of uv, that is a scalar. And it has the following properties. 1, positivity. 2, that the vector inner product with itself is equal to 0 if and only if the vector is equal to 0. 3, additivity in the first slot. 4, homogeneity in the first slot. And then 5, conjugate symmetry. We also define the inner product space as a vector space along with the inner product on V. And we talked about properties of the inner product space. We will go through these other topics in our next video. So in the meantime, that's it for this video. Thank you for watching.